Hey guys, have you heard of a new architecture from Google called Hope, which is really good at memory and self referential learning? Well, today I'm going to go into it. So let's dive in. A new architecture called nested learning, which is from Google, and it's kind of a new method which is better at self improvement and memory. And it's mainly correlated to how neurophysiology itself works, like from the human brain. So they have a few main contributions, like they are deep optimizers that they modified on top of Adam W and made a new optimizer which is much better in their scenario. And they also make their model much better at self-modifying itself. Like typical models aren't that good when it comes to modifying itself or learning new things, which they also have tried to solve. And the third thing is that they created a new memory system called the Continuum Memory System or CMS. And this one changes the traditional viewpoint of how long term and short term memory actually works. And combining the CMS with our self modifying sequence model, we create a new architecture called Hope. So, just to let you know, this paper is the summarized version, but they also released a bigger version of the nested learning paper. So, if you want to go more detailed, it's in that paper. So, continuing, here they show us the brain and also how they correlated to NL. So, as you can see here, the brain has different frequencies and brain waves. And so, in the first point, neuroplasticity is the brain's ability to reorganize itself via mechanisms like forming new synapses, strengthening or weakening existing ones, which is a limitation in normal LLMs where they can't like form new or reorganize its existing memories. So, in nested learning, what they did is that they made their architecture decomposed into a set of neurons, like they could be linear or MLPs, and each of them has their own gradient flow and context flow. And in the second point of what the brain does is that the multi-time scale updates is essentially in the brain we have multiple brain waves, and some of them are slow brain waves, some of them are fast brain waves. For example, the theta waves are slow waves while the gamma waves are fast waves, and normally the alpha or beta waves might come. They are the normal speed waves. And they happen in their own time. In ML, they also do this, but instead of using waves, they use things called levels, and then they separate their different types of memory updates in these levels with their own frequency. Like, for example, in the brain, it's like with hearts, but they also separate it with a different type of frequency, as you can see here. So this is some of the things that they try to correlate from how the brain works in neurophysiology into the two main things. So typically, AI research does multiple things to solve LLMs by either changing how their feature extractors work, but this limits their ability to actually process or learn from natural data. So they decided to go and look into deep learning, which has gone more better when it comes to actually learning things. Like even it's much better when it comes to specific tasks like chemistry or biology, games, and more. So in their scenario, they used the deep learning kind of methods by stacking multiple layers. And by doing this, they provided the model more capacity and more expressive power. Like in more complex tasks or even doing computations like flops and more, they are much better. But even when it comes to a deep design, there are still some cons. Like the computational depth of the model might not change with more levels, so their ability to do some of them might not be used. And the second one is where the capacity of some class of parameters might show marginal improvement. Like there might be more increasing of the depth or width of the model, but not that much improvement even while doing this. The third one is that when the training process might converge to a suboptimal solution, mainly due to the suboptimal choice of the optimizer or its hyperparameters. And the fourth one is that the model's ability to adapt to new tasks or continuously learn or continually learn might not be that good in normal models or deep learning models. So for this, they did their main contributions, like their optimizer, CMS, and more, to try to solve these issues. And here, they're mentioning how in typical models, when doing pre or post training, most of their context is like taken for that training, and later on it's not that good to update it. But they can update it with in context learning kind of abilities. But still, it would be expensive to do this type of solutions, so they decided to revisit how it even works. So they used an analogy to illustrate how LLMs actually work if we considered it as a person. So let's say that LLMs are a person and they may have a condition called anterograde amnesia, which is a neurological condition where in the future they cannot form any long-term memories after the disorder happens, which limits the person's knowledge and experiences to short windows. Like in LLMs, it's kind of like the LM can't store long-term memories that much, and they might not be able to change it. And if they did, they'd had to go to the short-term memories. So this is how they're considering an LM might be. Now, if we go down here, you can see that the human brain is very great and it does a good job into continual learning and context management, which is thanks to neuroplasticity, which is the brain's remarkable capacity to change itself in response to new experiences, memories, learning, or even when damage happens. And this is mainly due to two types of memories actually. A rapid online consolidation, also known as the synaptic consolidation, which is essentially like immediately learning something new. And then there's the second type of memory, which is the long-term storage. And like it slowly happens, but it stays for a long time, and it's really important memories. Like it even happens when we're like sleeping. So those are the two main things that happen in the brain that cause our brain to be good at getting memories quickly or slowly. Now coming back to the thought of anterograde amnesia, it says that the condition can impact both stages. So if in that case our LM might not be even good at online learning or like offline just slowly learning it. So if in that case we need to make it better at doing it in the first place. So now, soon enough, they'll be showing us how they're going to do this. That's why they're going to show us their notations. So let me just explain the notations. So X in the element is the element of real value, could be the input, and M is the state of the memory or model, M at the time of T, and T is the time. K is our keys, V is our values, and Q is our query matrices. And they also use bold lowercase letters with subscript like T to refer the vector that corresponds to inputs like T or multiple other inputs. Like under K, you can see K of T, V of T, and Q of T. So those are just basically that it's a vector. And then another one is that any distributions are considered as entities like F or P of F kind of distributions are there. So those are the main notations. And then they also use simple NLPs using what you can see over here with L, this thing over here. And like those are layers or residual connections as the architecture of memory module M works. And when it's needed, we also parameterize this memory module using this, which is theta of M, with multiple values, as you can see over here. So here you can see these are the notations. Now they're going to go a bit into their examples. So soon we're going to see two examples explaining us how it works step by step and what they're trying to do here. So in NL, like they're going to tell us some of their analogies, like how associated memories and all work. So if I go down here, they show us two things, the typical deep learning method and the neural learning module. In the typical deep learning layer, we can see that there's only one level here, and also when we see over here, there's only one gradient flow. Whereas when we see over here in NL's module, we can see that there's a level 1, level 2, level 3, with each of them with their own context and gradient flow. Also, when you see over here, level 1 is the slowest one, level 2 is the medium speed one, but they won't show this because it depends on the task. So they'll only focus on fast tasks or slow tasks. And depending on the task, it will either become a normal speed. And we don't have to do a separate logic for that. So you might not see this, but they're just showing us here. And level 3 is the fastest one. This is kind of like in the brain, the gamma waves are much faster, and the theta waves are slower, and this could be like a alpha or beta wave. So also one more thing to note is that you might see that level 1 or level 3 is kind of like fast or slow based on that, but that works in neurology. So in machine learning, sometimes you may get confused because they might denote level 1 as the fastest and level 3 as the slowest, but that's fine. And there's no actual difference with it. And in pre-training, which is what we consider level 1 as here, so they're considering level 1 as pre-training kind of. And now they're going to explain us one of the most importantest analogies, which is their associative memory. And this happens like when I see a water bottle, I might remember the brand or something to some place that I visited maybe. So in those scenarios, it's an associative memory. Seeing something like I see my eyeglass and it reminds me of a place we visited and bought it. So those type of memories can happen. And it's good when it comes to LLMs because once you get one memory, you can interconnect that memory to other memories. So this typically happens in the human learning, but we can also do this into the human brain. And also, before they show us how they actually show it in machine learning, they just want to make it very clear that learning and memorization is two different things. Because when learning comes, learning is just a process of getting a memory, whereas memory is a neural update caused by an input. So these are two separate things, okay? So that's basically the difference. Now they're going to show us how it looks in machine learning. So in their scenario, they're telling us that K over here is going to map to V. And how this works is that like my first memory could be the key, and then I'd get the value, which is my second memory. And though this might seem kind of weird if you think of it in neurophysiology, but it's the best way to correlate it into actual machine learning. If you think of it, our model itself is basically training to get better at, mapping our keys to values. So that's why they're telling, given a set of keys and values, associative memory is an operator of a map of keys to values, which they also show an equation over here for. So hope you got what associative memory is. Now, when going down over here, we can see that the memorization process, which is what they're trying to do, will be explained soon on how they actually do it with examples. So if I just go down here, not only that, they'll also try to make their own optimization process later on. Now, this is the first example that they're going to explain us of how a single layer MLP might be trained for a task of T and a dataset of D. And our one layer MLP is our W that we can see over here. And this is all optimized by the objective, which is L over here. And we're also using gradient descent. And this training process is equivalent to this optimization problem over here, where we can see our one layer MLP, and then we kind of just loop through it and find the best value that we could get from this. Okay, so now we can see that, okay, fine, this is the typical way of doing it, but we also want to use gradient descent on top of it. And when we do that, we get this result, this equation over here. So now, well, our goal is not to use a typical method, right? So what they're doing is that they decided to show us how associative memory works in everything. Even the typical gradient descent itself uses associative memory. So they reformed it into a method that we can, into an equation where we can see over here how the associative memory actually works. And here we can see multiple variables, and you might not understand these, but let me explain that. So here you see U. So what is U? Well, U is an LSS or local surprise signal. And why is it called a local surprise signal? Well, it's called that because in neurology, it's basically like local surprise signals, in the sense like surprises are errors. And in machine learning, we call them errors, but in neurology, we just call them surprises. Okay, but what is exactly a local surprise signal? Well, it's basically what like when we find an issue with our model, we are supposed to fix that. So our U tells us how much distance, or it's basically the gradient with respect to the loss. So it tells us how much better we have to get, or what's the path that we have to take to fix this. So that's what U is. And then we also have our existing variables, and then we use m equal to w to parameterize the memory, as we saw in the notations before. And then they create this new reformed method with u and their normal layer, and then they try to make it much better with the gradients. And then if needed, they'll penalize it if they have to. So that's basically how they reformed it. Okay, but if our main goal is to do memory, then we should mainly go on to that, which is exactly why they've shown us how to do it by replacing gradient descent algorithm with a momentum-based solution to work for memory. So here you can see there's a W over here, which instead of the previous values like W, we're using more of M for memorization. So here we can see there's more of M's because we're trying to make it better for the momentum kind of methods. So now we can see that, okay, fine, this is the base method, but we also have to redo it, like reform it, just like we did before over here to make it much better and show us how associative memory actually works. So here we can see how associative memory works when reformed. Okay, so now given this formulation, we can interpret this in two ways. A keyless associative memory that compresses our gradients into parameters, or associative memory that learns how to map data points to their LSS value. So basically this tells us that it's a two-level method, like slow updates or fast updates. And they also created their own type of process called the FWP, or the fast wait programs. And basically it's where the wait updates process like very slowly. But when it comes to any any memory kind of updates, it's very fast to do this, or momentum updates are very fast to do this. Now, concluding this example, we realize that it's like a gradient descent is like a one-level associative memory that learns how to map our data points to its corresponding LSS value. And the second thing that we learned is that gradient descent with a momentum is a two-level associative memory. Like when we update our weights or when we update our momentum weights, it's much different when it comes to the typical method of gradient descent. So in our case, actually outer level updates, like when it comes to level 1, it might be an outer level update, which is more slower, but inner level updates like memories are very fast to update. So we understood that from the first example. Now we are going to go a little more into how they actually do this in their scenario. So in this example, they explain us how the MLP module uses linear attention instead in this case. And then they try to train this one layer linear attention for a task called T and on a sequence of D of train, while trying to optimize the objective for L with gradient descent again. Now, recalling the same unnormalized linear attention formulation, we get a bunch of variables over here that our notations are k of t, which is essentially x of t or our input, to multiply with w of k. And then v of t is again x of t with w of v multiply. And it goes on the same for q. And then we also have M, which in this scenario is a matrix valued associative memory, as we can see over here. And so basically the definition of that is through taking their previous one and then adding their V of t and K of t and then transposing that. And that's basically what their matrix valued association is. And then we have Y of t, which is like our prediction that we're trying to do. Now continuing, we can see that we are trying to map these values. And over here, we can see a Hebbian value over here. This is the classical Hebbian value that they did. But to relate it into machine learning, they also created a more indirect version of Hebbian. And in case you don't know what Hebbian is basically the analogy of how when neurons fire at the same time, they wire at the same time, like associative memories wire, like when one memory comes, the second memory comes, like related. So that's what they tried to do over here with Hebbian law. And then they put it over here with gradient descent and they create this equation over here. Now, actually, you might have not seen any updates till now, but if you think about it, when we are using the projection layers itself, we are actually updating this. Like, it would be an outer layer kind of update. Over here, you can see that it's telling that we itself are updating it with the projections. So next, we are going to go a bit more deeper into this architectural decomposition. So now we realized how we can do it with two-level optimization process, which also coincides with the FWP interpretation. But in practice, we need to use a more powerful optimization algorithm to train our model. Or we might need to use a more powerful recurrent update rule for our memory. And for a simple example, we can assume we use gradient descent with a momentum to train a linear attention model. And in the above examples, we see how the linear attention component can be decomposed into two nested optimization problems. So here we can see that the model can use two-level optimization, like how they shown us in their previous graphs, where the inner level is like compressing the context with gradient descent, and the outer level optimizes these projection layers, like when we saw before W of V, W of K and W of Q and all, those are actually projections which are being optimized. So now we're going to go a bit into their actual nested optimization problems, and the previous ones were just examples. Even though we went through all of this, we haven't actually explored how the hierarchy-based methods could work, like levels, slow levels, fast levels, or medium levels work, actually, like in the brain, with frequencies. So for this, they explained us over here that if we have a component called A or B, which can be a parametric component or a non-parametric component. And in case you're wondering, what is parametric or non-parametric components, it's essentially just a thought of, imagine a painter. A experienced painter is the parametric component and they use their memories of how they should paint such strokes. But whereas a person without a parametric memory or anything would not notice and had to write temporary notes of what they had to do, but none of this would be stored. Which is why parametric memories or components are much better at doing this. So now they're going to explain us how they actually conditionally do their frequencies. So if we see over here, they have an operator which is this operator, and essentially what they mean by this operator is that the first value over here that they just dummy use a dot for would be faster than the right side item. So now they're going to tell us that if our first memory A is faster than B, and then we can denote that with A is faster than B. But this happens in only two situations. One is that if our frequency of A is greater than the frequency of B, then it would definitely be faster in their scenario. And also, just to tell you, when we use a frequency, it's denoted with F, and then it's a component below it. You can see. So the second condition is where the frequency of A is equal to the frequency of B, but the computation of B's state of time requires the computation of A's state. But if in case you're just confused about that, it's just the fact that if B is dependent on A, like for example in associative memory, the B's value might be dependent on A's value to create B itself. Those situations could also happen. And this could happen at a time called t. T is our notation for time. So in this definition, there is also another situation where A might not be faster than B and B might not be faster than A. In those situations, A's frequency and B's frequency are the same, which indicates that their frequencies are the same and update at the same time, and they also have the same frequency. But it could still be independent even if it's at the same time. Now, how do we separate these exactly? Well, we need to separate them into different levels, right? So they use multiple conditions to do this. Like they have one is where the components could be in the same level and have the same frequency update, and the second one is where higher the level, the more lower the frequency would be. And that's another situation. And based on this, we can separate it into different levels, which is how they separate it. So that's how they separate this into a different hierarchy, like how the brain does it. Now, going more deep into their optimizer, they just added a small section to tell us about how they're going to begin the neural learning module itself. So they're telling us that a neural learning module is a new way of representing a machine learning model that shows the model as an interconnected system of components, each with their own gradient flow and context. And this is very similar to deep learning, but with these changes, they make it even more better in memory self-editing itself and storing its levels, and all of these is much better than deep learning. And also, this nested learning is basically allowing computational models that are composed of the multiple multi-layer levels to learn from and process data with different levels of abstraction and timescales. So it essentially means that each level in nested learning has their own levels, and they either is more better computationally because of their capacity due to their deep learning traits. Next, they're going to show us how they do it in optimizers as learning modules. So over here, if we recall how the gradient descent method was done with momentum, we can see this equation over here, where matrix or vector of m of I is the momentum at state of I, and you may be wondering why isn't it t? It's okay, it's just a notation change. And alpha, which is our adaptive learning, with eta of I as our momentum rates, respectively. And if we continue, we assume that our adaptive learning would be equal to 1. And the momentum term can be viewed as a result of optimization for the following adjective like this, with gradient descent over here. This interpretation shows that momentum can indeed be a meta-memory module, and that it can learn to memorize its gradients into parameters. And building on top of this intuition, they also modify Adam in their bigger paper, their larger version of this paper. They also show this in section C.4. And so if we continue, they're going to show us multiple extensions, like new methods that they're trying to do, like a more expressive association, expressive objects, expressive memory, and so on. So starting with more expressive association. So how can we make more expressive association? Well, as discussed earlier, the momentum is a valueless associative memory, means it can also not have a value, so it has limited expressive power. But to address this issue following the original definition of what associative memory itself is, we can let the value parameters be having their own new parameter value. And just to simplify this is the typical way of doing it. What they added is this parameter p over here, in which they can store new parameters. And when combined with gradient descent, it looks like this equation over here. And this is equivalent to preconditioning the momentum of gradient descent, but it isn't preconditioning actually, but it's similar to it. And preconditioning means that a momentum term is an associative memory that learns how to compress the mappings between p and our gradient term. So essentially that's what preconditioning is. So preconditioning can also improve the expressivity of the method that we've seen before. So that's essentially how they make it much better. And also when we accept new functions of gradients, for example, Hessian is one of them, we can make it more meaningful when we use it. And Hessian essentially is just like a function that tells us how to improve our slope in gradient descent, and more methods can also be used. The next extension that they do is the more expressive objectives. Like as discussed, we can see that we have a Hebbian-like update rule, which can cause the memory to be less effective. But just to let you know that this only happens when we are doing a dot product similarity on the Hebbian-like update rule. Otherwise, it won't happen. But in these situations, we can easily solve this by using L2 regression loss for measuring the corresponding key value mapping. And so we can simply solve that issue by adding L2 regression. This is also based on the delta rule, so it allows the momentum to better manage its limited capacity and memorize the series of past gradients, which can also help us in the future. Now the next extension is for better memory, which is important. So as discussed earlier, we saw that the momentum can be viewed as a meta-memory model that can use a linear layer, like a matrix value, to compress the past gradient values. And due to the linear nature of how momentum itself works, only linear functions of past gradients can be learned by its internal objective. So to increase the learning capacity, one alternative is to change this into MLP. So most of this will change the linear matrix to MLP itself. So it has way more capacity than before. So also, not only that, they refer to this variant of their optimizer as the DMGD, or Deep Momentum Gradient Descent, their new gradient descent method. And then, okay, fine, we changed it into MLP, but still building on top of the perspective that we just saw, in which the momentum as a neural architecture, one common technique that they use to enhance the representation power of the momentum memory module is to use nonlinearity. So to speed it even more up, they use Newton-Schultz method to make it even more faster, which they denote with sigma over here, sigma, which you can see over here. The main difference that they add is only with the sigma that they add inside this Newton-Schultz function, which is why it's much more faster. Now, going beyond the backpropagation, as we've seen before in section 2.1, the pre-training process and backpropagation is a form of associated memory, where input data is mapped to the surprised or predicted output. So based on this, the associative memory perspective of the same equation would look like this. And as they discussed in Appendix C of the bigger version of the paper, the above formulation can also ignore the dependencies of data, like X. So to extend it to a even more powerful formulation, where it considers the dependencies of data points, which is extremely important when we use an optimizer in token space, as they are also not independent and they also have dependencies like from different memories. So in these situations, they also use a L2 regression objective with one step of gradient descent as follows. Over here, you can see in this equation, they use one step of gradient descent plus L2 regression. And with these changes, we can see our new formulation simplified over here. And later, when they create their optimizer, they can use this as the internal optimizer of their hope architecture, which is their main point of this entire paper, their hope architecture. Now here they also tell us that every architecture backbone consists of two main things, a working memory module such as attention, and then another one is our feed forward layer, like typically MLP, that views information across features and acts as persistent memory or a knowledge storage of a pre-training phase. But from NL's perspective, pre-training is the phase that's in their outmost layer of the learning module and is updated over even its own limited context flow. So the best thing to do according to their continual setup, such as pre-training phase, is that it is rarely updated, but even if they update, it would take a lot of context. So they decided to create a knowledge storage which will store this data over time whenever they update, which is much better because then they have more capacity to store other things. As you can see, they suggest a knowledge storage feed forward for each level or frequency domain. So now what we have is that we have a definition of frequency. And from this, they create their new memory system called continuum memory system, which is a chain of MLP blocks, such as this MLP block over here, that keeps on looping in an array. Like for example, when you see Y over here, it's just a bunch of MLP blocks. Like when we see in the deep learning architecture, it had multiple blocks. In their scenario, they're using multiple blocks. And each of them is associated with one chunk size. Like each of them will have their own chunks. So if in that case, we'd have a chunk for every single block or MLP block that we have. And from this, we have the parameters of the levels MLP blocks each time. So our theta of our levels each time will be updated on every chunk. So this is essentially what hoop architecture is. And based on this, they mentioned that this hoop architecture is actually a self-referential learning module based on the Titans or previous paper that they referred to. So self-referential learning is basically like referring to its previous past or learning from their previous experiences. And if we go down here, we can see how those chunks actually work. Like over here, you can see chunks over here. And so this is how hope in deep learning works, and this is how typical transformers in deep learning works with their FFN and attention. Whereas in their scenario, they have a low frequency, mid frequency, or high frequency. And this is how hope works, and this is how transformers typically work when they use chunks. And they have more space to add more chunks in hope than how transformers works. And also to see the performance of how they work, you can see over here their performance charts, which is better in some of the tasks than other models. So that's actually how hope works, and it's really good when it comes to deep learning because deep learning itself has many limitations that has been resolved in this paper. So in conclusion, hope is a really good architecture at storing memories and to update itself, to modify its mistakes, and to add new memories. And it's basically a really good self-referential model with its new nested learning method. And I hope you understood how hope works. So see you next time. Bye!